as I mentioned last time, in general, my plan is for you to have everything you need to for the problem set covered by Friday at the latest. There'll be a little bit of dependence on Friday after the problem set comes out, but not a lot. But because this is the first problem set, and I want to make sure you got a real feel for the course, in order to have enough material, I put one problem on the PSET, which is going to be covered today, and that is the topic of persistent data structures. And the idea behind persistent data structures is one that nowadays we live with all the time. It's basically version control. So, we're all used to this idea of a data structure where you perform various update operations and you interleave them with query operations. And the query operation asks you about the state of the data structure after having performed all of the updates you've already performed. But it's very natural if you put yourself in GitHub land or in the mind of version control to ask, well, why can't I ask what the state of the data structure used to be, right? It would be nice if I could ask questions about what was the minimum yesterday, right? Or what was the successor of this key 3 days ago, right? So that's a really natural thing to ask for. And I mean, if you go farther and think about the kind of forking we do on GitHub, you might also even want to say, suppose that 3 days ago I had inserted this other item into the data structure. What would the minimum be now? Right? So you might actually also want to perform updates to things in the past and see how those updates propagate through the present time. Okay? Long before we were using version control so heavily, this idea was explored. The initial paper was by Sarnak, and who would the other author be? Tarjan, of course. Who wrote a paper called Planar Point Location using persistent trees. And this was in 1986. And it appeared in the Journal of the ACM, which is the flagship journal in computer science. It's where the very, very best papers on any topic are supposed to appear. So they use this term persistent to talk about these data structures that you can access their past history. Okay? And so I'm going to tell you about a general purpose technique for taking any data structure and making it persistent. Then I will talk to you about this particular application of that, where you take a standard binary search tree and make it persistent, and you use it to solve a fundamental problem in computational geometry, which is not at all obvious what the connection between these two things is, but we will soon see them. So again, the core idea is to query and sometimes update past versions of your data structure. And Sarnak and Tarjan kind of developed this taxonomy. They talk about ephemeral data structures, where you can only access their present state. They talk about partial persistence, where you update the present, but can query the past. And then there's full persistence, where you can update and query the past. Okay. And their paper sort of really, it covers even full persistence. However, when you start updating the past, as all of us know, this creates very strange problems with the time-space continuum. You have to start talking about multiple worlds, right? And it just gets a little more complicated to talk about without really adding any sophistication, any new ideas about how to do it. So I'm going to teach you about partial persistence. If you want to understand about full persistence, you can go read this paper, and there's a follow-on paper with some more authors that I also mention in the notes. And as I said, what they come up with is a general technique for any pointer-based data structure. Which really means almost everything, right? If you think about our data structures, you know, our trees, our graphs, heaps, search trees, so on and so forth. Essentially, what you have is a collection of nodes which are of fixed size with fields, some of which are values, keys, or numbers that you want to put into the data structure. Some of those fields are pointers to other nodes. And essentially, any data structure that we implement, it's about, you know, having a collection of these nodes, which are linked together by pointers and which store values that are relevant to the data structure. And anytime you perform a data structure operation, the data structure turns that high-level operation into a series of updates, of reads and updates to individual fields and pointers in the data structure, right? And so the idea that Sarnik and Tarjan figured out how to do is how to make those individual low-level updates persistent. So they're going to create persistent updates to the pointers and other fields in the nodes of the data structure. And since you make each of those individual updates persistent, it means that the high-level operations of the data structure also become persistent. Make sense? So we don't need to worry about the details of how a particular data structure works. We will sometimes take advantage of it, I'll show you, but we don't need to worry about it in terms of the general implementation. All we do is figure out how to make individual field and pointer modifications persistent. So that's going to be our goal. Now, to make this concrete, I'm going to focus on trees. Okay. Again, what they do applies to any data structure with these fixed nodes with many pointers and so on and so forth. But trees simplify the story, in particular because every node will have at most one node pointing at it. And so that will be the focus of the lecture today. Okay. So with that in mind, any thoughts on how you can achieve persistence on a data structure that is a collection of pointers and other fields, right? So how do we change change the nodes, right, the individual nodes of the data structure, to remember all of their past history? Yes?
A linked list save all the past values.
Great. So the obvious thing to do, again, obvious now with all the version control that we do, is to keep some sort of log of changes, right? So one idea is to log all changes to any field, right? So essentially, we can replace every field with an array of all its historical values. I know you said linked list, but let's consider which of those will work better for us. This is known as the fat nodes method for obvious reasons. Okay. So if we imagine having, an array or linked list of values for every field, how do we simulate the standard operations of the data structure? Well, we need to transform every read of a field has to become a read at a given time from the record of all the values that have ever occurred in that field, right? An update now doesn't overwrite the field. It becomes some kind of append of the latest value to the log of all the values, right? And so if we provide these richer reads and updates at the individual field level, well, that lets us now perform the data structure operations, right? So for example, if somebody tells you, I want to, I have this persistent binary search tree, and I want to perform a search for the following key, well, now you have to add a second argument, which is when you want that search to happen, right? You're looking back in the past and searching at a particular time. And how will I implement that search given that I've enriched the individual nodes? Yes?
Just do like the binary search?
Exactly. Basically, at each node, right, I arrive at the node, and I know I'm performing a search in the binary search tree, but there's a specific time I'm searching at, and so I need to look at the value of that node, or the value of the field of that node, at my search time, right? And so this is why I'm going to use an array instead of a linked list, right? Is that given that fixed time, I can use binary search within the array in order to find what value was stored in that field at the time that I'm asking about, right? Now, the fact that I'm using an array makes updates a little bit more complicated, right? Because every once in a while, I'm going to run out of space in the array. But this is very elementary algorithms. If I just double the size of the array every time I run out of space to give myself more space and copy everything over to the bigger array, that doesn't really change the amortized cost of any of my operations. That's all covered. So we're not going to worry about that update cost, right? So the append is very straightforward. It just costs me the order one time to add the new value. And so that's no different from the normal way of working with the data structure. But what happens with the reads? So previously, I would just look at a field, and I would have the value. Now I'm instead performing a binary search. And so the time that it takes for me to look up the value of a field is now the log of my time range, right? I'm going to assume that time is treated as an integer that ticks up every time you make a modification to the data structure, okay? So t will represent the total number of modifications. I mean, you could also use clock time if you want to. It doesn't really matter. But there are we will say that there are t modifications that happened, and so that is going to add a log t to the time to look up a particular field, okay? Now, if the time to look up a particular field increases from constant to log t, what does that do to the time to perform operations on the data structure? Right, so previously, searching in a binary search tree took time log n. Now what is it going to take? Yes? Log n times log t. So what we're going to get is a multiplicative slowdown in all operations. So for example, the order log n that we get for binary search tree operations or for heap operations, right, becomes order log n times log t, right? And from one perspective, big deal. It's just a log factor. Who cares about a log factor? But the answer is that people who design data structures care a lot about a log factor, right? Because in data structures, it's always about the logs, right? We just spent a lecture and a half figuring out how to change something from log n to 1, right? And if we now decided to make a persistent Fibonacci heap, God knows why you would want to do that, but if we decided to make a persistent Fibonacci heap, all of a sudden our runtime for decreased key would become log t, and we would have just lost the wonderful improvement to constant time that we had before. So in data structures, you think about logs as being substantial, and it's kind of disappointing that you get this log t slowdown in order to achieve persistence. This led people to think about a different idea called, well, let's just talk about copying. So as an alternative to keeping a log in each field, okay, you could imagine the following, which is a little crazy, but let's just think about it. Suppose that every time I make an update to the binary search tree, I just make a full copy of the new binary search tree. Okay. Easy to do. Right? What does this do to the runtime of our query operations? How will I implement querying to the past if I have a new search tree for every single time step? Yes?
You have to go look through your list of all the copies of the tree, and so it's like an additive factor instead of a
Exactly.
multiplicative factor.
Now, I still need an array of, say, the roots of trees by time. And it's still going to take me order log t time to find the right root. But once I have found the right root, it's just a regular tree, right? And it's back to order log n time to descend that search tree, for example, right? So this is an additive slowdown instead of a multiplicative slowdown. And since a lot of our operations tend to cost log n time anyway, adding a log t is really no big deal compared to multiplying by log t. Okay? So this is great in terms of queries. What is the downside of copying the entire search tree every single time I do an update. Yes? Memory, right? So that's certainly one of them, right? Space, right? So space now has a multiplicative factor of n, right? Sorry, of t, because I'm making t different trees, each of size n. There's a second problem, yeah?
It takes a long time to copy the tree.
Exactly. Also, update time goes crazy, right? Also, sorry, now the update cost increases to order n per operation, no matter how fast the underlying operation was. So we get great queries at a terrible cost of updates. And this is actually not unusual. There's often this kind of trade-off, right? That the harder you work at update time, the faster you're able to make your queries. OK, so this kind of full copying is terrible. So let's look at a slightly more sophisticated idea called path copying. So suppose that I have a certain binary search tree that looks like this. It can be any old tree. Again, this is general purpose, but let's just make it concrete by talking about binary search. And suppose that I want to insert a new item into the binary search tree. Okay. I could copy the whole tree, but if you think about it, a lot of the tree is not actually affected by the insertion. So maybe I can save some time, save some space, by only copying the parts of the tree that care. So what parts of the tree actually care about the insertion that I just made? Which parts even notice that insertion? Yes?
The path from the added vertex to the root.
Exactly. Only the path from the root to the added vertex sees any change. So what I can do with path copying is say, OK, I want to insert a node here. That means I need to get a new representation of what used to be an ancestor with an empty child, right? I need to create a new ancestor that actually points at me, right? But instead of making a copy of the other, let me draw a line here. Instead of making a copy of the other leaf, I can just use the original leaf because it hasn't changed. Okay. Now, of course, since I have made a change to this node, it means that the world is different for this node, and so I'm also going to make a copy of this node. But here too, instead of copying the whole other subtree, I'm just going to link to the original because it hasn't changed. So now, instead of making a full copy of the entire tree, I only need to copy this path from the root to the leaf. Make sense? And so clearly, this is a big improvement, both on the additional space I'm using and the amount of time that I need to spend. Notice that I can still use the array of roots trick. I mean, the root's going to get copied on every single update, right? Because it always sees a change. And so I'm still going to be able to have this additive log t to find the appropriate root. Once I do, I'm going to descend through nodes that don't even know that they're part of a persistent data structure, right? They look just like the original nodes of the data structure. It's just that sometimes they're pointing into historical versions of it. Yes?
Why do we need log t to find the root?
Because we need log t to find the root when you are answering a query about an update at a particular time. I mean, again, if you're really just having an update every single time step, then you could just use an array and index directly into the array. But if you have a mixture of queries and updates, right, you might not actually have an update on every single time step. And so you need to pack those update times efficiently, or if you're using wall clock time to track when updates are happening, then you can't just index into an array, and instead you need to actually search for the predecessor of the time that you're querying about. Okay? So we're all clear so far? All right. So path copying is nice. It still has this additive log t query time, and the update time and space have gotten better. But it's not clear how much better. It depends now on the shape of the tree, right? The length of the paths. So query, we have this order log t additive. Notice that you can still do queries in the present without any slowdown at all, right? You don't have to search for the present time. It's at the end of your array. But if you want to query the past, you have this additive cost. Updates are now the length of the path. And, well, that might be good if you have, say, a balanced binary search tree, but actually at the end of this lecture, I'm going to start talking about unbalanced binary search trees, and then the path could be very long. Also in Fibonacci heaps, the path could be very long. So this doesn't provide guarantees of any improvement of performance at all. So this is where Sarnik and Tarjan got really smart. So they argue that, in a sense, they want sort of a middle ground between these two ideas. Okay? So path copying is, in a sense, too aggressive. If you're just making one update, why copy the whole path, right? You could instead just store one updated value in a fat node, right? And that's not a big deal. That doesn't slow things down very much. So the problem is not with all fat nodes, right? It's just with very fat nodes. A sort of just a pleasingly plump node would not be a problem, right? So let's combine these two ideas. We're going to allow slightly fat nodes. And we're going to combine that with path copying when those nodes get obese. Okay. And in particular, we're actually going to be quite strict about it. We are going to allow each node to have exactly one extra time-stamped field to hold the first update to that node. Okay? So in this overflow field, right, when an update happens to this node, we will specify which field we updated, what time we updated it at, and what the new value was. So there's actually 3 values associated with this overflow field. Okay? And we will use it for the first update. But then, on the second update to this node, we will copy to make a new node. Okay. But here's what's very important. The new node, right, we're going to make a copy of that new node to hold the updated value, but that new node is going to have a new and empty overflow field. Okay. So again, right, if we look at this binary search tree that I was managing over here, right, the first update where I add this leaf, I'll just store that information in the overflow field of this node. Now, the next time I make an update, if say I change the value in this leaf, I'm going to look and I'm going to see that the overflow field is full in this node. So at that point, I'm going to make a new copy of this node, and I will store the pointer to the new leaf in this overflow, in the right pointer of this new copy. But that will leave me a new empty overflow field in this copy that I've just created. Okay. Now I also have to think, when I do make a copy of this node, what else do I have to do? I can't stop here. Yes?
The parent?
Right. Since I now have a new node here, I have to make sure that the parent can point to this new node at the appropriate time. So I may have to go to, I do have to go to the parent of this node and update its child pointer, which may involve storing a value in the overflow field of this node. Or if this node has a full overflow field, I may have to make a new copy of this parent. Okay. And of course, when I make a new copy of the parent, that may force me to make a new copy. That forces me to update the grandparent and possibly make a new update of the grandparent. So does this remind us of anything we saw last time? Yes?
Cascading?
The cascading cuts that happened in Fibonacci heaps, right? That we're trying to sort of maintain something locally, but this may cause disruptions that cascade all the way up the data structure. So we're going to do the same thing here. When we have this second update, which involves making a new copy, this is going to force us to update a parent field either by using its overflow field or by a cascading copy. So we've kind of worked out what's going to happen on updates. Let's think about how we will implement queries in this data structure. So again, a query involves starting at the root and walking down to find whatever node it is that we're looking for, which means we look at the values of certain fields. But given this representation, what does it mean to look in the value of a field, right? This query involves which may be pointers. And so how do I do that? Again, we're simulating a single pointer access. As a low-level operation, a whole series of these provides the overall data structure operation. So how do we implement this single pointer access? It's not very hard, but I want to make sure that people understand how this is working. Okay, so I'm told, here's my node. I need to look at the left child pointer. How do I do that? Yes?
Check the overflow time. Is the overflow time all time or not all time?
OK, so I've checked the overflow time. What else do I have to check about that overflow field? Remember, I can use the overflow field for any field, right? So if I'm told to follow the left pointer, I need to check, is there something in the overflow field? And is it the left pointer? And is the update time earlier or later than the time that I'm querying, right? So is it the same field? Is it non-empty? Actually, non-empty should come first. Right? Is there something in the overflow? Is it the same field? Is the update time earlier than the query time? And if all three things are true, then I use the value in the overflow field. Right? If any of them is false, I just use the value of the original pointer or original field. Yes? And what's critical is that this is a constant time operation. And so is update, right? For updating, well, we need to look and see if there's room in the overflow field. If there is, we use it. If there isn't room in the overflow field, we make a copy of a node. But again, these nodes are fixed size, so copying a single node is constant time. And so either way, update is constant, and query of a single field is also constant. Okay? And so we already have, just from the fact that queries are constant, that the query time has the same nice order log t additive slowdown, not multiplicative. But the question that remains is, what kind of update time do we get? Why are we doing something so complicated? Well, it's because we're going to get a much nicer result on the update time. And the analysis that I'm going to do applies equally to the update time and the update space. How much of each is used by an update? And again, what I'm asking is, how much time or space is used by an update to a single field? In a data structure update, you'll do many of these field updates and several field queries, right? And so we're going to have to multiply whatever our slowdown is or our space cost is by the number of primitive pointer updates that are performed. Okay? So what is that cost? Well, surprise, surprise, we're going to do an amortized analysis. Right? If you think about it, worst case, right, we could have a tree where all the overflow fields got filled up. And once all the overflow fields are filled up, when I do an update to a leaf, I'm going to have to copy all the nodes up to the root. So in the worst case, my update time could be very large. But I'm going to show you that the amortized update time is small. Remember that we define a potential function. And now we get, and that potential has a value at every moment of the data structure, at every step. And we define the amortized time and space used by the ith operation is the real time or space plus the change in potential. And we saw last time that because this telescopes when you add it up, right, that if we bound the amortized cost of a series of operations, we are also bounding the real cost of that series of operations. So all we need to do is define a suitable potential. And again, the idea of the potential function is that it measures the deferred work, right? And in this case, that deferral is a deferral of the time to do the update, but also a deferral of the space that you may need to use to store the new values, right? And so the question is, what kind of potential, can we sort of work towards this intuitively, might represent, right? We want something that is large when we are going to need to do a lot of copying, and small when we are not going to need to do a lot of copying for a while. So what might measure that in our data structure? What sort of directly represents a copy that's going to happen really soon? Yes?
Number of nodes which have overflow fields.
Good. So a full node, right, a plump node, is bad, right, in our modern society, right? So if the overflow field is full, then we're going to need to copy that node the next time there's an update. So that's a problem, and so that should represent a large potential. Okay? But if we think about it, not every full node is a potential problem. Yes?
Is it just like the most recent full nodes, like the
Good.
full nodes that exist at the current time?
Good. It's sort of full nodes that exist at the current time, right? If a full node is in the past, then under partial persistence, we're not going to change it. It's never going to need to be copied, right? So, so we're saying, one way to deal with the modern obesity problem would just be to kill all the obese, right? And then we wouldn't have a problem anymore. And so it's the same here. If you push it all into the past, you don't have to worry about it. So our potential function is simply going to be the number of full, which is to say their overflow field is in use, active nodes. So full just means the overflow is used, and active means that is reachable from the current root, whatever the current root time is. Okay? So let's think about using that as a potential. Okay. Sorry, just for consistency with my notes, I call this live in my notes. So with this potential function, let's think about the amortized costs and we don't need to think about queries. We already know those work just fine. Right? We're just talking about the amortized cost of an update. And again, we can focus on just a single field, just an update to a single field of a single node. Okay. So if we want to think about updating a field of a single node, we need to consider two cases, right? So one case is where so which case do I want to do first? If the overflow field, if the overflow field is empty, then what's the real space cost involved in storing a value into that overflow field? Yeah? It's free, right? So the real space that we use in terms of the number of data structure nodes is 0. The real time that we use is 1 for storing the value in the field, right? What about the change in potential? Yes?
The change in potential is also 1.
Good. The change in the, well, you say also 1, but it's different from the 0 of the space change, right? So we have just filled an active node. So we've increased the potential by 1. Okay. Now, so that means that the amortized cost in both cases is order 1. So now let's consider what happens if the overflow field of the node is full. Then what is the real cost? What do we have to do if the overflow field is full? Yes?
Copy and update.
Good. So, but let's focus on this node for the moment, right? Copying this node means we need a new node, right? So the space and the time for both of these things are 1 to do the copy. But what can I say about the change in potential? What do I do after I copy the node? Yes? Right. So after I copy this node, I update its parent. Right? Or sorry, yes, once I copy the node, I update the parent to point at the new copy. Right? Which means that the node that I am copying becomes dead. Right? Right? So I had a node which had a full overflow pointer live. I killed it and made a new node for the copy, but it has an empty overflow pointer. And it's that new node that is now going to be reachable from the current root. And therefore, I just gained a unit of potential, which means that the amortized cost is 0 in both space and time. Okay? Now, after I recognize the 0 amortized cost of making this copy, I might have to do a cascade, right? I have to update the parent now, which may mean storing a value in the parent field or making a copy of the parent, depending on the state of the parent. But the same argument applies about the amortized cost of dealing with the parent, right? Under what circumstances am I going? So, you know, we have these two analyses, right? If the overflow field is empty, then it costs me 1. If the overflow field is full, then it costs me 0. So let's think about the cascade now, right? I update my first node, right? One possibility is that its overflow field is empty. In that case, it costs me 1. If its overflow field is full, then dealing with it costs me 0. And now I can go deal with the parent, right? The same argument applies to the parent. If it's empty, then I pay 1 at the parent. If it's full, I make a copy, and that costs 0, and I have to go to the grandparent, right? But the critical observation is that the only way I'm going to pay 1 is when I have an empty field. And at that point, I stop, right? So it's exactly like cascading cuts, right? So with the cascade, we kept going up and paying 0 for the cascading cuts until we hit a node with an empty mark bit. And at that point, we paid 1. Same thing going on here. We started our leaf. We start copying and filling fields. And all of that costs 0 until we get to an empty field. And when we reach that empty field, we pay 1, but we also stop. So however long the cascade was, we only pay 1 amortized cost for the final node that we update. And that means that the amortized cost of the entire cascade is order 1. Is that clear? No questions? Super. So that's kind of the end of the story for persistent data structure implementation. Right? We've just shown that the amortized cost of a pointer update with the entire cascade is order 1. Now, we multiply this by the number of pointer updates, but we're multiplying by a constant. So asymptotically, this doesn't matter at all. So whatever the space and time bounds are for your persistent data structure, right? We have an additive t-space for the array of roots. But no more. We have an additive log t time for the same reason, to find the appropriate root. And we have a multiplicative order 1, space and time increase to get our versions. Yes?
How do we have only our phone space multiplicated if we're like making new nodes as we go?
That's exactly what I just proved here, right? What this analysis has shown, I did two things at the same time. I proved to you that the amortized time per field update was order 1. And I also proved to you that the, I'm sorry, I know what you're saying. So this is additive t-space for the array of roots. And let's see, what do I want to say here? So in a particular data structuring operation where I make a number of field updates, I use order 1 space for each of the field updates, right? Not for each data structure update. Because again, a single data structure update is a series of field updates. Okay. So this is optimal, right? You can't really hope to do better than this if you're planning to actually store all of the updates. It takes that much space, and it doesn't hurt your query time at all. Any questions? Okay, so I'm now going to show you a really cool application of this idea, as I said, within computational geometry. But let's take a 2-minute break first so you can stand up and jump around a little bit. Remember, if everybody's sitting, I'm going to assume you don't need a break. Yes?
So this trick was for partial persistence, right?
Yes.
Is it possible to achieve similar results for full persistence?
Mm-hmm. It's all in the paper.
Oh, I guess I need to read this. Question about the other one. You said that we can't know what's the update length of the path, but isn't it like updating a node takes at most or takes at least the length of the path?
Well, that's the problem, right? If you do path copying, your update cost is the length of the path, and some data structures have extremely long paths.
Yeah, but isn't it that to update a node, you need to find it in that structure anyway, so it costs the length of the path?
To find it, but the path copying comes with a space cost as well. So it's true that it's optimal for time to do the update because you already spent that in reads. Although in general, reads are generally a lot faster than writes, so it's good to keep the number of writes small. But really, the issue is space.
But isn't it here at the worst case? Can't we say that we will have a log n factor space at the end of the test structure anyways? Because we have O1 space for each field update.
But we have log n paths. Yes, but I'm going to show you a trick in our particular application which actually overcomes that.
Oh. Also, here for partial persistency, it doesn't matter if some cost of the operations were like amortized, not like real time.
Well, so that's the thing. This does turn every data structure into an amortized data structure, even if it was originally a real-time data structure. So that is one of the penalties that you pay.
No, I mean that if you had a data structure, you had some amortized operations. In case of partial persistency, it doesn't matter.
Right.
But for full persistency, like most of them couldn't be like.
Well, again, so this is one of the reasons I do partial persistence is that it's complicated to even use vocabularies to talk about what you want in full persistence. But I think they do a pretty good job of it in the paper.
Wait, so actually, if some of the cost was amortized, we can still do full persistence?
Mm-hmm.
Really?
Yeah.
Once you just have some like long operation, you
it would roll back and do it again many times. In this case, the structure itself would work long.
Yeah, so again, this has to do with the definition of what does it even mean to be amortized if you have multiple worlds, right? Do you need to be amortized per world, or do you need to be amortized over all of the worlds simultaneously?
So in
Right.
each path, the sum should not be too large.
That is certainly easy to achieve using these techniques. I can't remember what the story is if you're looking at all of the worlds at once.
Want to look at like total sum of all worlds.
Yeah, I'm not sure. Okay. All right, let's resume. Once again, I got some great questions during break. Once again, I want to discourage you from doing this. Ask these questions during class. That's why we're having class, is so you can ask questions. And when you ask the questions during break, I have to remember to repeat them to all the students in the class so that they can get the benefits of the answers as well. And the problem is that I have a terrible memory, and so I'm going to forget a bunch of the questions that were asked. And I've already done that for today's topic. Somebody did ask whether it is possible to get these same bounds for full persistence, and the answer is yes. And like if you go to the papers, you can read how they achieve not just updates, not just queries in the past, but also updates in the past with the same order one update multiplicative cost for updates. Okay, so now let's look at a kind of cool application of this. And this is to the problem of planar point location. And I have to define that for you. This is actually a kind of computational geometry problem. And computational geometry is something that we will spend a week, maybe a bit more on towards the middle of the semester. You know, it's not all that different from the sort of algorithmic problems we look at in general, sorting and searching and such, except that instead of the primitive objects being like strings and numbers, the primitive objects that your algorithms operate on are points and lines and hyperplanes and so on and so forth. And we assume that you have access to the natural basic operations, like asking if a point is on a line, or asking if two lines intersect each other, and if so, where, right? Or computing the distance between 2 points. Now, there's actually a little bit of weirdness underneath some of these assumptions because, for example, the distance between 2 points might be irrational even if the points are rationally specified, and so you can't actually store the actual distance. And so we sweep all of this under the rug and just assume that these basic operations are available to us, okay? In practice, of course, you round off, you keep track of precision and such. We're not going to worry about any of that. We're just going to assume all of the basic geometric operations. So we assume that all of these basic geometry operations like intersecting two lines, or computing the distance of points, are order 1. And we use that, and we use those to implement more sophisticated operations. And what we're going to look at is basically the computational geometry generalization of binary search. So what we're going to assume here is that we have a division of the plane into polygons by some collection of lines. Oh, I shouldn't use vertical ones. That will confuse the algorithm. All right, so we have this division of the plane by line segments, and we get a query point. And we have to say which polygon contains it. The edges, and in terms of the complexity of this problem, we are going to assume that these polygons are made by n segments. Or they could be lines that extend forever. Okay. But we will assume that everything sort of ties off neatly. You know, if you have a line with another end, it doesn't really break anything into polygons at all, and we just won't worry about it. Okay. Yes?
Polygons, are they convex?
No, there is no restriction on the form of the polygons. Okay. If I want to, let's see. That's just fine. Okay, I can have any shape of polygon that I want. Okay. In computational geometry in general, you always triangulate things so that you only have to worry about triangles, but that's not important for this particular application. There are a lot of special purpose solutions to this problem, but I'm going to show you how you kind of get it really fast just by using persistent data structures. So to get there, let's look at, this is a two-dimensional problem. Let's look at the 1D version of this problem. What is the 1D version of this problem? Yes?
I actually had a question first, which is, are we saying that polygons don't overlap?
Correct. This
Okay,
is a
so-
division of the plane into polygons. Okay. So what's the 1D version? Yes?
Is it just a line with a bunch of points on it?
Exactly. The 1D version is that I have a line, and I have a bunch of points on the line. Right. And again, I get a query point. I get a query point, and I want to know which polygon, in other words, which line segment, is my query point in. Right? How do I answer that question? So this line with points dividing it into segments. And now I want to know which segment the query point is on. So how do I answer it? What sort of data structure do I use to answer that question? Yes? Yeah, I could use binary search, right? And so again, if I'm given all the points in advance, I can just put them in an array and use binary search to figure out where the query point is among them. If I expect to be inserting and deleting points on the line, I could use a binary search tree, right? And then I would search within the binary search tree for the predecessor and successor of the query point, okay? And either way, it's going to cost me order log n time, right? So I'll use a binary search tree, okay? And that means it's going to cost me order log n time to find the location, and it's going to take me order n space to store that binary tree. Okay. So the question is, can we generalize this idea to 2 dimensions? And if we do generalize this idea to 2 dimensions, what does it do to the time and space of this simple approach? And so taking this approach of thinking about 1D and then trying to generalize up to 2D is very common. It's what distinguishes computational geometry from a lot of other algorithmic sub-areas. But there's a natural thing to do here. Imagine, I drew these points kind of carefully, that I took this 2-dimensional arrangement, and just wherever there's a segment endpoint, I sort of projected that down onto a line, which is remembering where are all of these segment endpoints. Okay. So I draw these altitudes wherever there is an endpoint of a segment. And this has a nice feature of dividing my polygon arrangement into a bunch of slabs. Okay? So what we're going to do is we're going to drop an altitude from each segment endpoint. Okay. And this is going to divide the plane into slabs. And I claim that thinking about the whole arrangement as being broken up into slabs like this sort of decomposes the problem nicely. So if I want to find which polygon the point is in, I can do that in two sort of natural steps, right? I can first find the slab that the point is in, right? How do I do that? Yes?
Search like the 1D.
Right. That's just using the binary search tree, right? Once I know what slab it's in, what do I need to do? Well, I've got these segments dividing up the slab into vertical regions, right? And so I need to figure out where among these segments is my query point vertically. But I claim that this is an easier problem than thinking about the whole polygonal arrangement. What makes it easier to just think about one slab? Yes? Exactly. I can again binary search. Right? What's critical is that in the slab, there are no crossing lines. Which means that every line is either above or below every other line. There's a total order. So I can use binary search to find the lines that are directly above and below the query point. Okay. And so I can't do this with direct numeric comparison, right? There's no specific number for this line, but given the query point, I can ask whether the line is above or below the query point by doing some very basic algebra, right? And that's enough to let me binary search among the segments. Okay. So I transform this two-dimensional search problem into two one-dimensional search problems. Okay. So if we think about implementing this directly, okay, seems like it's going to work, but it's going to have some downsides, right? So if I want to be able to binary search in each of the slabs, right, I'm going to need a binary search tree for each slab. Right? So I'm going to start with a binary search tree for the x-coordinates. And then I also need a binary search tree for each slab. So what can I say about the costs for this data structure? Well, in terms of time, it's great, right? How long does it take me to answer a query? Yes?
Oh, you have login time for the x-coordinates and plus login time for each slab.
Exactly. So the query time is order log n for the x plus order log n for the y, which is just order log n. So it's matching the query time of a one-dimensional search problem for what is apparently a much harder problem. Okay. But what's the drawback of this approach? Yes?
Tree for each slot, and that might be really bad.
Right. So how bad is it? How many binary search trees am I going to make? About n, right? Basically, every endpoint of a segment is going to cause me to make another binary search tree, right? So space-wise, I'm looking at n binary search trees, right? So that means that I'm going to be taking n squared space, which is crazy. You never want to use n squared in modern computers because n is always so big. And it's not only space, it's also the construction time. Right? I have to build each of these binary search trees. So that's a disaster. Okay. So what are we going to do about this? Well, this is where persistent data structures come to the rescue. And it really just takes a very small change in perspective. Instead of thinking about having these two spatial coordinates, x and y, let's think, I don't know how many of you read Flatland, but let's think about x as time. Okay, so instead of saying that we are living in a two-dimensional world and answering queries about locations of points in this two-dimensional world, I'm going to imagine that we are actually one-dimensional creatures living in time. Okay? So at a particular moment in time, our world is a vertical line. Okay? And that vertical line has segments going through it, but all we see are the points on that vertical line. And as time evolves, our vertical line moves horizontally. Right? So the world is a vertical line, moving from left to right, okay, where x is the time coordinate. Right? And what we see is segments passing through our world. Or intersecting our world. As points in our world. Now, what happens to these points as time progresses in our world? These points are caused by segment intersections, but what do we perceive? Yes?
Their position changes.
They move, right? Unless the segment is horizontal, how we're going to perceive a segment is as a moving point. Okay? So besides moving, something else also happens with these points. Yes?
Direction.
Not if they're a segment, right? If it's a segment, then the point is just, it's following actually a constant velocity in our world. Yes?
Two of them become one and one becomes two.
Good. So the point is, points will appear or split and disappear or merge, right? Okay, so we have these points appearing, then moving at a constant velocity, and then disappearing. And we also have these queries which basically ask, where in my world are you at this particular time? In other words, which point are you above and which point are you below? Right, so I'm basically trying to answer a one-dimensional search question based on the particular time at which a query happens. My 1D search is a y-coordinate search. Okay? So I'm not really solving a two-dimensional problem anymore. I'm asking instead, I want to be able to search for the vertical position, right, between which 2 points are you, of a point between other points that are moving and appearing or disappearing. What kind of data structure might make that easy? There's really only, there's only one answer, right? I mean, what have I been teaching today? Right? We'll use a persistent data structure. And that's really the whole answer, right? So when somebody tells us, here are the segments, okay, we implement a persistent binary search tree, and we evolve time, right? So given the segments, we are simply going to order the endpoints by x coordinate, which is time coordinate, right? And we'll then do a series of inserts and deletes into the binary search tree in time order. And when we're done, we'll have this persistent binary search tree. So now, point queries become queries of this binary search tree at the time, in other words, the x-coordinate of the query point. Now again, it's worth noticing that these points that we've inserted into the tree, they don't have a fixed y-coordinate. They have a y-coordinate that's changing based on exactly what time it is, but they do have a fixed order. They don't cross, right? If 2 points meet each other, then one of them vanishes, right? So we don't have to reorder the tree. We just need to remove things from it and insert other things into it. Okay. So does everybody understand how this solves our problem? Then let's just look at the runtime and space cost. So I haven't told you what kind of binary search tree we'll use. Okay, let's use any old balanced binary search tree. So for example, I'm sure a lot of you have seen red-black trees. Those are popular as a particular implementation of a balanced binary search tree. Right? Because it's balanced, we're guaranteed that the query time is always, and update time are always order log n. Right? So if we use this as the underlying structure, what is the time for a point location query? Yes?
Where log n plus log t, which in this case is log n squared.
Sorry, what was that last? Log n squared?
Yeah, so log n.
All right, so it's 2 log n, right? It's not log n squared, right? So we have to query for the time, which is order log n, which is order log t. And then for the specific binary search tree at that time, which is order log n. But since we have n segment endpoints, t is equal to n, which implies that this is also order log n. And so our overall query time is order log n. Great. We're matching the one-dimensional solution and the sort of make lots of copies solution. What about the overall space cost for this data structure? Yes? How come? So we're doing n updates, right? But these are data structure updates. So now we need to ask how many primitive field updates happen during a data structure update. And we just said, it's a balanced search tree, right? You just update nodes on the path to the insertion or deletion. So there are order log n updates, field updates. Per structure update. And each of those field updates costs order 1 space and also order 1 time during construction, right? So this would give us an order n log n space and construction time bound. So pretty fantastic, right? By using persistent data structures, instead of spending n squared space to maintain all of these copies of different binary search trees, we get away with n log n space to hold all of the same information, right? Because of our clever versioning. Now, just to squeeze a little bit more out of this, if you think about, if you go back and look at red-black trees, their updates are very specific, okay? Red-black trees are based on these notion of having these red-black bits, right? And you use these red-black bits to tell you when you need to do a rotation of the tree to preserve balance. Well, you definitely need to remember the structure of the nodes, which parents and children, so that you can do the binary search. But you don't actually need to remember the red-black bits, right? After you're finished building the data structure, they don't matter anymore, okay? So we're not going to bother with persisting the red-black bits. We're only going to persist the child pointers in the red-black tree. And a feature of the red-black tree, which makes it very nice here, is that you only ever do 1 rotation per update. Okay? So in fact, there's going to only be 1 persistent update per data structure update. And that drives our space down to order n, 1 per update. So in fact, this is exactly the same time bounds as you have for the one-dimensional problem, right? Sorry, twice as slow, because you do 2 binary searches instead of 1 binary search. But this is an optimal data structure for this interesting and fundamental point location problem that we get kind of just by throwing a persistent data structure at the problem. One postscript, another thing that you get out of persistent data structures is papers in SOSP. So about 20 years ago, I taught this lecture, and a couple of systems students in the class said, hey, why don't we build a whole file system using persistent data structures? And so if you go look, if you're a systems student, and you want to go look for PFS, the persistent file system, it came from here, from just saying directories are also trees, and if we use a persistent data structure for them, then we can store all their old versions without taking up any more file space. Thanks. So next time, the topic will be splay trees, which are one of the weirdest and most magical data structures in all of computer science. So I will see you then.